You know, for most of my life, even when I was deep into studying physics, I had this one huge idea completely wrong. I always thought that when you throw a ball, it just follows one single path through space. I mean, it seems totally obvious, right? But it turns out that's not just wrong, it's fundamentally wrong. And today, we're going to dive into the absolutely mind-bending reality that everything is exploring every possible path all at the same time.
So that brings us to the big question, right? Is that gut feeling we all have about how things move actually correct? When anything, a tiny particle, a huge planet, even you walking across a room, goes from point A to point B, does it really just take one single clear-cut path? Well, as we're about to find out, the answer is a big, spectacular no.
Okay, to really wrap our heads around this, we're going to start with a classic thought experiment. It's one of those things that proves that the most obvious path, a straight line, isn't always the fastest one.
So, picture this. You're a lifeguard on a beach, and you spot someone in trouble out in the water. Now, you know you can run way, way faster on the sand than you can swim. So what's the absolute quickest way to get to them? Well, if you go in a straight line, you'll spend a ton of time swimming, and that's slow. What if you run way down the beach first to minimize the swimming? Nope. That makes the total distance way too long. The actual fastest path, the optimal one, is somewhere in between. It's this perfect angle that balances your super fast running with your not so fast swimming.
Okay, but here's the crazy part. This isn't just some fun brain teaser. This exact same logic is what nature uses for light. You've seen this a million times. When a beam of light hits water, it bends. That's called refraction. And why does it do that? Because it's taking the fastest possible path, just like our lifeguard. It travels a little bit farther through the air, where it's faster, to spend the least amount of time slogging through the slower water.
And this is where things start to get really weird. I mean, a lifeguard can look at the situation and figure out the best route, right? They can think it through. But how does a beam of light know the fastest path before it even starts? It's like it has a map of the future. Classical physics just kind of shrugs and says, well, that's just the rule. But that doesn't explain the how, does it? And that very question, that little mystery, is a clue that points to a much, much deeper and, frankly, stranger reality. So, to find the answer, we actually have to jump in a time machine and go back to the late 1890s, to Germany. And the motivation wasn't some deep philosophical quest. Nope, it was the hunt for a better light bulb. The German government wanted to make the most efficient light bulbs in the world, and this very practical industrial problem, well, it accidentally blew a giant hole in the foundations of physics. See, scientists were trying to understand a pretty basic thing, how hot objects glow. It's called black-body radiation. And when they tried to come up with a theory to explain the colors of light you'd get, it worked. Kinda. It worked perfectly for the long wavelengths, like red light. But when it came to the short wavelengths, like ultraviolet light, the theory predicted that a hot object should be blasting out an infinite amount of energy, which is, well, it's impossible. This total, spectacular failure of the theory got a fittingly dramatic name, the ultraviolet catastrophe.
And the person who finally cracked this impossible problem was a physicist named Max Planck. But here's the thing. He wasn't some wild-eyed revolutionary trying to burn down the old physics. In fact, he was a really conservative physicist. He only found the solution because he was completely backed into a corner.
And his own words just say it all, don't they? He called it an act of desperation. He said he was ready to sacrifice every single one of his previous beliefs about physical laws. I mean, imagine that. He tried everything that the established rules of physics allowed, and absolutely nothing worked. So, he decided to break the rules. And his desperate rule-breaking idea was this. What if energy isn't a smooth, continuous flow? What if it can only be given out or taken in tiny little chunks, little packets? He called one of these minimum-sized packets a quantum. And just like that, the quantum idea was born. The idea that deep down, the universe isn't smooth, it's pixelated. Here's a great way to think about it. The old classical views saw energy as a smooth ramp. You could have any amount of energy you wanted. You could be anywhere on that ramp. But Planck's idea completely changed the picture. It turned that ramp into a staircase. You can be on the first step, or the second step, or the 10th step, but you can never, ever be hovering in between the steps. The energy had to come in these specific whole number multiples.
And you know what? By throwing in this one desperate idea, Planck's formula suddenly matched the experimental data perfectly. It worked. But to make it work, he had to introduce a new number, a new fundamental constant of nature we now call Planck's constant, or just h. And here is the really spooky part. When he looked at the units of this new constant, they weren't units of energy or momentum or anything familiar. They were units of action. That same kind of obscure idea we started with, the thing that describes the path of least time, all of a sudden action wasn't just some mathematical curiosity anymore. It was right at the heart of this brand new physics.
Now, Planck himself probably just thought this was a clever math trick to solve a problem. But his little quantum idea, it turned out to be the master key that started unlocking every single major mystery in physics at the time. It set off this incredible domino effect that would totally rewrite our understanding of reality itself.
And boy, did things move fast. So in 1900, you have Planck. Just 5 years later, in 1905, a young guy named Albert Einstein says, hey, maybe it's not just the emission of energy that's quantized. Maybe light itself is made of these packets, which we now call photons. Then in 1913, Niels Bohr quantizes something else, another form of action actually, to finally explain why atoms are stable and don't just collapse on themselves. But the real game changer, the next giant leap, came in 1924 from Louis de Broglie, who had an idea that was even more radical than all the rest.
De Broglie just flipped the whole thing on its head. He thought, okay, if waves like light can sometimes act like particles, couldn't particles, like electrons, sometimes act like waves? And he went for it. He proposed that everything, and I mean everything, has a wave nature. Every single particle in the universe, from a tiny electron all the way up to a basketball, and yes, even you, has a wavelength.
And this wasn't just some abstract philosophical thought. It gave the first real, physical reason why Bohr's model of the atom actually worked. Why could electrons only be in certain specific orbits? Well, according to de Broglie, it's because an electron's wave has to fit perfectly around the nucleus, like a snake eating its own tail. It needs a whole number of wavelengths to connect back on itself smoothly. When it does that, it creates this beautiful, stable, self-reinforcing pattern called a standing wave. Any other orbit, and the wave would mess itself up and just fizzle out.
Okay, so let's pause. Particles are waves. And that wave nature is the thing that finally, completely shatters the idea of a single path. And this is where we bring in the final hero of our story, the brilliant and charismatic physicist Richard Feynman, who took this wave idea and followed it to its ultimate, absolutely beautiful and bizarre conclusion.
Now, you've probably heard of a famous double-slit experiment, right? The one where a single particle somehow goes through two different slits at the same time? Well, Feynman asked a simple question. What happens if you add a third slit, or a fourth, or 100, or 1,000,000 slits? What happens if you just keep adding slits until the wall between them is completely gone? Well, what you're left with is just empty space. And the conclusion is just unavoidable. If a particle has to explore all the possible paths through all those slits when the wall is there, then it must still explore all the possible paths when the wall is gone. So, to get from point A to point B, a single electron, or a photon, or literally anything, is simultaneously trying out every single path imaginable. The straight one, the curvy one, the one that goes to Jupiter and back, the ones that go backwards in time, all of them, at once.
So if that's true, why on earth do we only ever see one path? This is where Feynman's genius really shines. He said to imagine that for every single one of those infinite paths, there's a little spinning arrow, a phase. Now, for most of the really wild, random paths, the amount of action changes so erratically that these little arrows end up pointing in every possible direction. When you add them all up, they just cancel each other out. It's called destructive interference. But, and this is the beautiful part, for the paths that are really, really close to that one special path, the path of least action, their little arrows all end up pointing in basically the same direction. They add up. They reinforce each other. That's constructive interference. And that's the path we see. It's not the only path, it's just the one where all the possibilities agree.
I know. This sounds like some wild, beautiful mathematical daydream. It can't possibly be how reality actually works, right? Can we prove it? Can we actually catch light taking one of these so-called impossible paths? The answer is, astoundingly, yes. And the proof is just as clever as the theory.
Okay, so how do you prove it? Think about light hitting a normal mirror. We're taught it bounces off one specific spot, right? Angle in equals angle out. But according to Feynman, that light is actually hitting and bouncing off every single part of the mirror at once. We just don't see it because all the weird paths cancel out. So to prove it, we can use a special mirror called a diffraction grating. It's basically a mirror with tiny little grooves etched into it that are designed to strategically block certain light paths. And by doing that, we stop the cancellation from happening. And what do you see? Suddenly, light appears to be reflecting from places that classical physics says are totally impossible. It's the smoking gun. It's direct proof that the light was taking those other crazy paths the entire time.
And this is the big takeaway. This isn't just some quirky little quantum rule. This whole idea, the principle of least action, is the bedrock. It's the foundational framework for pretty much all of modern physics. We're talking classical mechanics, how planets orbit, how you throw a baseball. We're talking electrodynamics, light, magnets, the whole deal. Special relativity, even the standard model of particle physics, all of it, at its deepest level, comes from this one single principle. Nature will always find the path that minimizes this weird little thing called action.
And that brings us right up to the cutting edge of physics today. The grand quest for a theory of everything. Well, it's not really about discovering some new particle or some new force. It's about finding one single master equation for action. One perfect recipe that, when you apply this principle, gives you back every law of physics we see in our universe. It's the ultimate mystery, isn't it? What is the one simple thing that the entire universe is trying to do?